now that we have learned how to calculate force due to gravity based upon the distance between two objects, we're not just stuck on the surface of the Earth using our gravitational field strength of 9.8 meters per second squared, we can use the idea that work equals the integral of the force in terms of its radial distance. So since we're dealing with planets here, we're going to talk about the object being some radial distance above the surface of the Earth or any other planet. This applies to all objects. And also remember that work is equal to the negative of the change of the potential energy. So if we can figure out what the work is due to this new form of the gravitational force equation, we can figure out what the potential energy equation is. So force was equal to gravitational constant, the mass exerting the force, the mass experiencing the force, divided by r squared. And we're going to integrate in terms of r. So I'm going to pull the g, the m, and the m out front, since those are constants. And I'm going to rewrite r 1 over r squared as r to the minus 2. I just find doing integrals a little easier that way. So we end up with a negative r to the negative 1 power, because we added 1 and then divided. And we should probably evaluate this between r1 and r2. So r1 and r2. So that we end up with work is equal to the gravitational constant, the mass experiencing, and then we can say, bring the minus sign out front, and say 1 over r2 minus 1 over r1. So remember, potential energy is final minus initial, so we get that the potential energy is equal to a negative gravitational field strength, mass exerting the force, mass experiencing the force, divided by the distance between center to center of the two objects. This means we have to rewrite our conservation of energy equation. So we can just consider gravitational potential energy and kinetic energy. So now this equation allows us to deal with objects that are moving very far above the Earth's surface. So either moving far above the Earth's surface or in what we consider outer space. Since we're ignoring air resistance, there isn't much difference between the two in our sort of calculations. And the reason why we need to do this is remember that g is equal to our gravitational field constant times the mass exerting the force divided by r squared. So if we continue to treat potential energy as mgy, the further we get above the surface of the planet, the more inaccurate this number becomes. So by using this new form, we're encompassing and dealing with the fact that g is changing as we are moving above the surface of the Earth, or moving towards the surface of the Earth. So this allows us to extend how far above the Earth's surface we can actually do problems than just near the surface of the Earth. It also allows us to do problems for other planets because, remember, 9.8 meters per second squared was specific to near the surface of the Earth. So now we can look up the mass of the moon and the radius of the moon plus whatever distance from the surface of the moon that you're dealing with, and do this problem using conservation of energy of something falling towards the surface of the moon.